From this lecture, we will start the discussion of Fourier analysis. The Fourier analysis is nothing but representing signals using another set of signals. So, why do we even want to represent a given signal in terms of other signals? This could be for different reasons. The main motivation for us is simply because for LTI systems, the convolution operation with which we describe the entire input-output relationship turns out to be a very complicated one that you must have seen from all the examples that we have encountered, right? So every time you have to do this integral and then compute the convolution, turns out to be a very difficult operation. Can we simplify this further? In fact, even if you want to implement this convolution in computers, even computers find this very complicated. It so turns out this Fourier analysis simplifies the computational complexity of convolution. So if you have to convolve two signals, even computers take more time to do the convolution than to simply take the Fourier transform and implement the convolution using Fourier transforms. So here what are we doing is we are using a tool known as Fourier analysis to analyze these signals and then represent them in a different form, where in the different representation it becomes easier for us to identify what is the input and output of a system. Okay. So our motivation to study Fourier analysis here is to simplify once again the understanding of systems. All we want to do is understand a system. That system for us is an electronic circuit. We want to understand that completely, and that understanding comes from trying to find out the output for any possible input. We already know that. We know it through convolution, but convolution is complicated. Let's try to simplify this, and Fourier analysis is going to help us. And how are we going to get to that? We are going to use an important property that we commented about in the last lecture, and that property is the eigenfunctions of the LTI system or the convolution operation. What is an eigenfunction? So if you feed in a particular signal or a function to a system, you get a scaled version as the output. You claim that this is an eigenfunction. That's the definition, right? Alright. Now we want to find out what would be an eigenfunction for our LTI systems. And we already saw that the differentiator and integrator have an eigenfunction which is the complex sinusoid. Will that also be the eigenfunction of LTI systems? Let's check that. So let's take an LTI system with an arbitrary impulse response, okay, and convolve that with our complex sinusoid. Now how do we do this convolution? Our usual convolution integral, we write it down. Now we can say that this is equal to e power j omega t. We'll just simplify this integral, h of tau e power minus j omega tau dt. That's what we have here. So if you notice here what happens, all we have done is just simplified this convolution integral, because t is not the variable of integration. You can pull it out outside. It is constant with respect to tau, so it comes outside. The moment it comes outside, that was the actual input signal. So if this was x of t, this is x of t, it comes as such. So if you observe this integral, it is not a function of t, meaning you want to find the output at a time t. It can be at 0 seconds or 10 seconds or 1 million seconds. At whatever time you want to find the output, this integral does not change. So if I want to find the output at t equal to 0, this integral is still the same. If I want to find the output at t is equal to 10, this integral is still the same, because it is not a function of t at all. So it is a constant value. This entire integral represents the area under this curve, and that is fixed. The moment you fix x of t, this is also fixed. So basically what is this? This is nothing but h of tau and x of tau theta. That's it. So this is the area under this, and that is all. It is fixed. Hence it is a constant. So the output now simply becomes a constant multiplied with the input. This is essentially the definition of eigenfunction, and hence complex exponentials turn out to be eigenfunctions of any LTI system. Okay, this is very, very useful for us. We'll see how this is useful. And not only this, complex exponentials are something much more than just being an eigenfunction. They are also orthogonal. See, if you see here, why should we even consider a complex signal? You can just simply convolve h of t with some e power at, okay, and it will still satisfy this property, which means any exponential is an eigenfunction, not just complex exponential. But why specifically complex? Why unnecessarily make our life complex? It is not unnecessary, it's because complex signals give us two other important properties which are useful. The first one is orthogonality. We spent an entire lecture discussing about orthogonality. So, complex exponential are orthogonal signals, right, which we don't get from the regular exponential signals. So, orthogonality is a very useful property. Once again, we will see why this is very useful and how this will simplify our life. The other important thing is the complex sinusoids are bounded, which means the amplitude will not grow to infinity at whatever time you compute. So, if you have an exponential e power at, if a is positive, as t increases, this goes to infinity. If a is negative, as t decreases, it goes to infinity. So, we have a problem with exponentials as they are unbounded and they need not be orthogonal. Whereas, if you take complex exponentials, they are bounded and orthogonal, which are very nice properties which will be very handy for us. So, hence, we will focus more on complex exponentials than on exponentials itself. And also, they are eigenfunctions of the LTI systems, which becomes more useful for us. Okay, so now we know eigenfunctions. Why are they even useful? Because if I feed in an eigenfunction to an LTI system, I know for sure that I need not do this convolution operation at all. Like I feed in an eigenfunction, let's call this some x of t. I just need to know this constant. I'll just multiply and then be happy about it. So, what if I restrict all our input to just some combinations of eigenfunctions? Let's say now I know that the complex exponentials are eigenfunctions, which means that I can change this frequency, right? So, here we did not specifically say what the value of omega is. Omega can be anything from minus infinity to plus infinity, omega can take any value, which means we have now an infinite set of functions or signals which are eigenfunctions of the LTI system. So, you can change this omega value. For each omega value, we will get one signal and they are all eigenfunctions. So, now I have infinite set of functions or signals which are all eigenfunctions or eigensignals of LTI system. Now, if there is some other signal that is given to me, let's say x of t, can I represent this as some scaled combination, some ai times xi of t, where these xi's are all the eigenfunctions? If I can do this, what is the advantage? If I can do this, then when I feed in this as the input to my LTI system, what essentially am I doing? I am convolving this with the impulse response, which is as good as convolving each of those with the individual impulse response. This is where the distributive property, linearity, everything comes into picture. Okay, it's not for no reason we studied those properties. So, we are using the linearity property, distributive property of convolution. But what is this? Because this is an eigenfunction, you don't have to sit and compute this integral convolution. You can simply say, okay, I know this, it has to be some scaled version, right? So, which means the output is simply going to be, see, we did not do any integration here, we just expressed the input in terms of the eigenfunctions, and then immediately we were able to find out the output also in the same fashion. So, all we had to do was multiply this coefficient that was present in the input with a different coefficient here, which are basically the eigenvalues, and we found out the output. Keep this in mind, this is something which we do repeatedly in Fourier transform. All you do is take the input signal, decompose this in terms of the eigenfunctions. Okay, when you decompose, what is this decomposition? Essentially, all you have to do is find these coefficients. That is a decomposition. And how do you find the output? The output is simply nothing but the multiplication of these coefficients with the eigenvalues and then putting everything together, we have found out the output. This is the main idea of all the Fourier transform. Decomposing an input, finding the coefficient, and expressing the output as a product of the coefficient and eigenvalue. Okay. This is the main idea behind Fourier analysis. It simplifies our entire input-output relationship. Instead of doing this, complicated convolution, you can just do this decomposition and this multiplication.